Hi everyone, my name is Stefan Reinauer, and I'm part of the Chrome OS coreboot firmware development team at Google. I am also the upstream maintainer of coreboot. So I want to talk to you a little bit about porting coreboot to the ARM platform. Generally, most of the things that Aaron already mentioned apply. There's some subtle differences that I'm going to talk about. So first, I'm going to go a little bit into detail about the current status of our ports. Then about the differences of ARM and x86. Talk a little bit about the boot flow, device configuration, and the situation with the payloads and bootloaders. So right now, coreboot is supporting a number of ARM chips, including the Exynos 5250 and 5420, the NVIDIA Tegra 124 Texas Instruments chip, and an Allwinner A10. Not all of these ports have been done by Google. The first three have, and some of the stuff is coming in from the coreboot community, who is showing a lot of interest in supporting more than just x86. And also, we've been working on supporting emulators, so we could test our system. Particularly, we've been working on a QEMU port, and just as of late, we started an effort to port coreboot to the ARM64 foundation model. So, mind you, porting coreboot to a non-x86 platform is not something exactly new. It has been done before. Actually, around like between 2000 and 2004, there was a PowerPC 64 port of coreboot. Back then, it was still named Linux BIOS. There was an Alpha AXP port at some point. As coreboot progressed, we had to get rid of those ports, and the platforms, quite frankly, died. So, however, now in the end of trying to unify our firmware strategy, we decided that adding ARM support to coreboot would allow us to basically have the same solution on all of our Chromebooks. This is basically what a typical x86 system looks like, a PC. There's a lot of dynamic stuff going on. Basically, if you look at it, there's PCI devices that can be automatically detected. There's RAM that's in sockets, which has holds its configuration data in SPD ROMs. There's an LPC bus with devices attached to it. There's USB IDE. All those things are dynamically discoverable. And so that's where a lot of the flexibility of the coreboot device model comes in. However, if we now look at the typical ARM system, most likely we have a system on a chip. We have soldered down RAM. We have pretty much every component sits in the chip. And it's not, there's not a big need to configure or to detect external components. There's also a boot ROM, which unfortunately on the systems we've been working on is not memory mapped. So we had to do some extra effort there. And some components like the TPM is not attached to the LPC bus, but for example, to the SM bus. So yeah, the differences in philosophy, I guess, between x86 and ARM is in the systems we're still seeing today is x86 tries to be very extensible. There's SPD, PCI devices, LPC, but we also have things like where we have to work around certain peculiarities of the chip, like caches RAM, and we have to make it even more flexible and dynamic. We have ACPI and system management mode. ARM systems are usually of a simpler design and like targeted for the low power market. There's in the systems we've seen today, there's a first level boot firmware in the SoC itself, in a mask ROM on the chip, that will start loading what we consider the bootloader or the system firmware. Basically everything that's part of the SoC is memory mapped at some fixed address, or it is attached to one of the bus systems. A nice thing we have in our ARM systems that we ported to is we have a certain amount of SRAM available, which is in this case also a requirement because we don't have a memory mapped system firmware. Up to this point, we don't have ACPI support for ARM. That might very well change with the advent of a UEFI on ARM64, but we see. And there's no system management mode. So I'll walk you through the boot flow really quickly. There's as I mentioned, there's a first stage bootloader in the SoC. Usually, this bootloader will load a silicon vendor provided second stage bootloader, which might be signed, which we, for coreboot purposes, we consider that part of the boot block. Then we have a coreboot boot block, which parses the file system, this CBFS file system in the SPI flash, to find its components for a boot up. That boot block will load the ROM stage just like on x86. ROM stage will jump into RAM stage, and finally the payload, which then loads the operating system. Stuff that the boot block does on ARM that's a little bit different than on x86 is we can set up a stack very early in the boot block because we have SRAM. We can load the ROM stage from the SPI flash into SRAM and execute it from there. But that also means we need, for example, a SPI driver in the boot block very early on to load the later stages. And then ROM stage is very similar to x86, basically there to initialize memory and then jump to the device configuration that happens in RAM stage. Again, like on x86, ROM stage got its name because it is executed in place from ROM. On ARM, it is just as the boot block executed in SRAM, which gives us a number of freedoms. And then the rest is very similar to x86. Here's our current example of how we use the SRAM. So there's roughly 380 kilobytes of SRAM available. You can see a little portion of it is reserved for the internal bootloader, the internal SoC firmware. Then we reserve some space for each of the stages. We reserve some space for the TTP buffers to set up caching in the system. We also, because we can't memory map the SPI flash, we have a CBFS cache where we on demand load certain blocks of the SPI flash and operate on it in this SRAM buffer. And then there's a stack and a little bit of amount of memory that is shared with the kernel to pass information to the kernel. The device configuration follows the same principle as on x86. However, we tried to do most of the setup of the components that we're using in the code, and so we're having very few parameters that can be toggled. And this example of the Exynos 5420, basically what we have is a setup of the display and the GPIOs required to drive USB. And everything else is basically set up exactly the same on all different implementations using that SoC. At the point when we're done initializing the hardware and we jump to the payload, the bootloader, I think we'll hear more about that later. We have a library called libpayload that contains a set of drivers and functions that are handy for all kinds of different bootloaders. This library is a BSD licensed, so it can be used in open source and closed source projects. And it provides an abstraction for payloads. In our case on ARM, we have to provide a number of drivers specific to each SoC. That might be like a UART driver or drivers for storage and flash and so on, timer implementation. These things, fortunately, on x86 were exactly the same over a large number of different CPUs. There's definitely more work to be done on ARM because the landscape is not as unified. And so on ARM, since our main goal was to boot Chrome OS on Chrome boxes and Chromebooks, the first and right now only working payload that we have is depth charge, and it boots a number of systems that we're working on internally. There's an experimental port of the open source bootloader Philo, which is not working yet though. And so if you're wondering where does the device tree that the kernel expects come in, this device tree is in the coreboot this scenario is provided by the payload. So the payload will contain a device tree to pass on to the kernel. And that's it. If you have questions, I'm here to answer them now. Yes? Excuse me, can you repeat, please? Mm-hmm. 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 Are you talking about verified boot in terms of like the Chrome OS? Mm-hmm. Mm-hmm. So the question is, U-boot provided a verified boot mode and a non-verified boot mode to allow booting arbitrary kernels. And is there a way of doing the same thing with coreboot and depth charge? And the answer is yes, there is a way. If you're going to developer mode on the system, you will still be able to boot an unsigned kernel. Yes?
More general related question to that. U-boot has an interactive props and a shell. Are there any plans or discussion about making that available in depth charge when you're not booting verified?
Yes, we are working on some features actually on that front. There will be a small shell that allows tweaking some of the settings and might be used for debugging. It's not part of depth charge in any way, the way we ship the systems, because we consider the console to be first bulky and an additional attack surface. But we do provide that for debugging, and we also are working on a GDB interface that allows you to operate depth charge through a remote debug system. Yes? I believe, why are we generating thumb instructions instead of ARM instructions? Okay, there you go. Well, Julius assumed it was faster, and since we have to store everything in flash, and flash memory is potentially limited, it is also smaller. That were our initial was our initial rationale.
I can understand that it can be smaller because the top instruction is only 16-bit for each kind of OP code, but why it can be faster?
If it has to come off eMMC, it's going to be slow. That's fast.
Right. So a lot of time that we spent during the boot process, basically coreboot typically boots the Chrome OS Linux kernel within like 500, 600 milliseconds after power on. And so even reading code from SpyFlash or eMMC, whatever, is a significant part of that boot time. And so making it smaller usually also makes it faster. I don't know much about why it would be faster beyond that. Sorry?
So if the code is smaller than the instruction cache, then also
Oh, there you go. If the code is smaller, the instruction cache can hold more instructions too. Excellent. That's true. Any more questions? Yes. So in the question is, why can't we skip the payload and load the kernel directly? This is actually the original, this has been done before, and it was the original design idea of coreboot back when it was called Linux BIOS. We stored a Linux kernel directly in Flash and executed it right from there. And then what, for example, kexec into another kernel or something like that. However, on ARM, a few more things have to be provided to the kernel, like the device tree, for example. And currently we don't have a mechanism to provide a device tree to a kernel in coreboot itself, because that is done by the bootloader stage. That said, we have also been experimenting with putting a kernel right into Flash. For Chrome OS purposes, we're most likely never going to ship a system like that, because the kernel is rather big, and so we want to have Flash space contain only the required parts to boot a system. But it can definitely be done, and it has been done in the past. For booting securely on a Chrome OS device, a depth charge holds a lot of knowledge about the verified boot process as well. And so we would also need to verify that the kernel that we're actually booting, is correctly signed. So it would add a lot of code to coreboot that is currently living in depth charge or verified boot. That's it. For development purposes, of course, you're free to put or non-Chrome OS systems, you can definitely put a kernel right into Flash. Any more questions? I think that's it. Okay, thank you very much.